Hello, very Merry Christmas if you're watching this video around December, or Happy New Year. I never know quite what to say on a YouTube video because this video will be available to watch even in the middle of summer. But at least at the time of recording, Christmas, got my Christmas jumper on. And it's lovely to be able to provide one more video before Christmas hits, and then hopefully on Christmas Eve I'll put some kind of Christmas quiz on the channel. So in this video we're going to be looking at the kinetic energy of quantum particles, and it's particularly interesting to do this because in classical physics, if something has zero velocity, it has zero kinetic energy. That's given by the classical equation often written in the form E equals a half mv squared, where if v is zero, E has to also be zero. And one might think that this rule, this idea that zero velocity implies zero kinetic energy, works for everything. But quantum mechanics, as it has a tendency to do, refutes this idea. In quantum mechanics, it is possible to have a particle with zero classical velocity, but positive non-zero kinetic energy. Now really the ideas of classical velocity and classical kinetic energy when applied to a quantum particle need to be used in quotation marks, because particles in traditional quantum mechanics are treated in such a way that we can't really apply the ideas of classical mechanics directly to them in a very general setting. So the video will start by talking about how we arrive at an equation often written in the form E equals a half mv squared for a classical particle, and then how that derivation or that sequence of logic can't be applied to quantum particles. We will then go into a fairly formal, at least maths-heavy derivation, proving that for a particular class of quantum particles, so stationary state particles, they have positive kinetic energy, so positive non-zero kinetic energy, but they have zero classical velocity, as the name stationary might imply. And then because it's such a strange result, to wrap up the video, I'll have a quick last bit where I describe how to think about the logic behind the quantum version of kinetic energy in terms of Heisenberg's uncertainty principle, which so much of quantum physics seems to ultimately hark back to. But anyway, wishing you an amazing day, and if you are watching this near Christmas, many festive wishes. But for now, let's get cracking with some quantum mechanics. A way to think about this beginning of our kind of video is a change of perspective. Because we're going to be looking to start with at the differences between how classical physics considers kinetic energy and why we can't take that definition and apply it exactly to quantum mechanics. And to help navigate through this slide, I've got a series of boxes, but I've labelled each of them with numbers, like the number 1 here, so it's easier to work out the order of the boxes when a few of them appear on screen. It's one of the ways I'm trying to improve content on this channel, making it a little easier to follow. So the confusion can be left to the physics. So to begin with, we're looking at kind of kinetic energy in classical physics. Now, in classical physics, we define kinetic energy as a path integral of the force acting on the particle and the displacement of the particle along some curve. Now, the curve I've taken to be gamma, that's just my symbol for the curve. So gamma is at the bottom of the integral to indicate that we are integrating over the curve gamma. And ds, where s is a vector, is a infinitesimal tangent vector along that path. So, like, it's kind of, if we borrow some language from special relativity, ds is kind of like the direction the particle is moving across the world line described by gamma at a particular point in its path. Now, this is a very formal definition. If you've looked at introductory classical mechanics before, you definitely might not have seen the kinetic energy expressed in terms of a path integral. And we can get around the path integral because the particle is changing its position along the path gamma with respect to time. So we can parameterize both the infinitesimal displacement vector ds and also parameterize the force F using the parameter t, where t is time. And evaluating the integral, where we are parameterizing F and ds in terms of time, leads us to the much more familiar equation for classical kinetic energy. And this equation does assume that the particle starts with 0 kinetic energy at time t equals 0. And then at time t0, assuming the force F is acting in the same direction as the path the particle takes, so F isn't at some angle to the path, but F is always parallel to the path, which is often the case if we're pushing and pulling something. If we're pushing something, we want to push on it in the direction we want the object to go, so that's a fairly common occurrence. But providing these things are true, this is the expression for kinetic energy. Now I'm using the symbol S instead of X to keep things general. I mean, we might consider the particle to be moving along the x-axis, in which case we can replace S with X, but to keep it general, I'm just calling the axis along which the particle moves capital S, such that the infinitesimal displacements along that path are ds. Now, we can't quite take this notion of kinetic energy and apply it directly to a particle retreating quantum mechanically. And that's because in traditional interpretations of quantum mechanics, at least, I mean, the pilot wave theory is an exception to this, but in traditional interpretations of quantum mechanics, particles do not follow a well-defined path. So we can't define a curve gamma along which the particle moves. So we can't evaluate the path integral we have in box 1 to arrive at our expression in box 2. And similarly in box 2 we have ds by dt evaluated at t equals t0. But if we don't know where the particle is, we can't evaluate what ds by dt at t equals t0 should be, at least in most cases. So we can't take the definition of classical kinetic energy and apply it immediately to all quantum particles. There is a connection between classical kinetic energy and the kinetic energy operator in quantum mechanics, which I'll come on to in a moment. But importantly, we can't take a very deterministic idea of classical mechanics where particles follow a set path gamma, allowing us to find the kinetic energy in terms of the gradients of that path. We can't take the classical ideas and apply it directly to quantum mechanics. Instead, with quantum mechanics, we're stuck with a probabilistic description of matter. And you get the probability by integrating over the modulus squared of the wave function. Now, the modulus squared is just the wave function times its complex conjugate. So we can think of the probability as the integral of the complex conjugate times the original wave function integrated over the path. So over the possible values of S within the region we are interested in working out the probability of finding our particle in. So quantum mechanics is very probabilistic. And just as a kind technical note about my notation, S is taken to be an axis defined by our vectors ds. And even if S is curved when we see it on the 2D plane, or rather I should say, even if the curve gamma is curved in a 2D plane, if we look at that curve very closely, then each segment of the curve will appear over a very short distance along the curve to be straight. That is to say, the curve is obeying Euclidean geometry, and therefore if you were living on the curve you wouldn't know it was curved. So we can think of our curve gamma as being intrinsically flat, like intrinsically straight, with no intrinsic curvature. Now that's a very technical note but worth putting, but it essentially allows me to consider S as a axis which is perfectly straight, just like the axes we are more used to dealing with, such as the x-axis or the y-axis. And that's because locally, so if you lived on the curve gamma, the curve gamma would appear straight, or at least there would be no way of telling that you were living on a non-straight curve, unless you were able to look at that curve from the perspective of a 2D or higher dimensional space. But the key thing is, as we can't in quantum mechanics say where a particle is exactly, we can't say what path it is taking, we cannot use the classical definition of kinetic energy and apply it to all quantum particles. And this is important because whereas in classical mechanics it would be a contradiction to say something has zero velocity but has kinetic energy, that does not apply in quantum mechanics, because in quantum mechanics we cannot use the equation in the blue box. However, that equation is helpful in leading us to an operator which will capture the essence of kinetic energy in quantum mechanics. In the last part of the video, we looked at why we can't take the classical definition of kinetic energy right over to quantum mechanics and just stick it to quantum particles and expect everything to work out well. So in this part of the video, we're now going to redefine how we think about velocity. Now, an important thing is that a quantum particle is traditionally described by a wave function, and that wave function is spread out over space. And for the purposes of this video, I'm considering the particle to lie exclusively along the s-axis. So our wave function psi takes in a value s and then outputs a number. We're saying that number can be complex, can be real. For now, it doesn't really matter. So how should we think about the position of this particle along the s-axis? S-axis, even when we can't pin down exactly where the particle is. Well, one thing that is done often in statistics is if you don't know the value of something, you work with the expectation value of it. You work with the average version of it. So the closest we can get to where the particle is within the context of quantum mechanics is the expectation value, or if you like, the mean value of S. And this mean value is weighted by the wave function. And so the mean value won't be along the middle of S in many cases. Regions of our s-axis where the wave function has a large amplitude will contribute more to the average than regions where the wave function has a small amplitude. And so if we're going to look at velocity, so the rate of change of position of our particle along our path S, the closest we can do in the context of quantum mechanics is find the time derivative of the expectation value of S. And to do that, we need an expression for the expectation value of S. And we find this using the general kind of operator structure, the kind of eigenvalue nature of quantum mechanics. And also, rather lovely, S is is describing position, and therefore the position operator S hat is just S, and that actually makes finding the average value of S really quite straightforward. So this would be the expression for the average, the expectation value of S for a quantum particle with wave function psi. Now all we have to do is differentiate our integral with respect to time, and that will give us a classical, or what I am calling the classical velocity of our quantum particle. And so we now have to consider whether the wave function psi will vary with time, and if so, how? Because the details of this will affect the partial derivative of the expectation value of S with respect to time. Now, it turns out for particles with stationary states, which you can also think of as particles with well-determined energy, so particles in well-determined energy states, such as electrons around atoms when not emitting or absorbing light, such as many examples of quantum particles. For particles in a stationary state, the position-based wave function, so psi of S, is a real function and is independent of time, so can be written without involving the parameter of time. And because it can be written without involving the parameter of time, the partial derivative of the of two terms in the integrand is just 0 if we're taking the partial derivative with respect to time. And also S is the position, S is the axis along which our particle would in a classical sense be moving, and even in a quantum sense, S is the axis along which the wave function exists, but it's an axis in space. And so clearly the partial derivative of S with respect to time is 0, and putting all of that together, we conclude that particles have 0 classical velocity. Now, it's worth saying this isn't the only way we can define velocity in quantum mechanics, but by classical velocity, I will mean that the partial derivative of the expectation value of position over time is our expectation value of velocity. I think it's the closest we get, at least mathematically, to the classical expression for the velocity of a particle. So we found that particles which are in stationary states have 0 classical velocity. But do they have 0 kinetic energy? Well, to answer that question, we're going to find the expectation value for the kinetic energy of a stationary state particle. So we'll use an equation that looks very similar to the equation we had in the blue box. But because kinetic energy is not position, the kinetic energy operator is not as straightforward to find as a position operator in quantum mechanics. So we're going to first get the kinetic energy operator, and then we'll use that operator to work out the expectation value for the kinetic energy of a stationary state particle. So our goal is to now get the kinetic energy operator, which we can then use to find the average kinetic energy of a stationary state particle. So, let's begin by thinking about what properties we would want our kinetic energy operator to have. So, the kinetic energy operator I'll denote with a hat above the T, because T is traditionally used in classical mechanics, particularly in the context of Lagrangian mechanics, to represent kinetic energy, and the tradition is we put hats above operators. We don't bother so much with position operators like S, because S, the classical variable, and S hat, the quantum operator for that classical variable, are the same thing. At least if we're considering a wave function as being a wave function describing the probability distribution across the S-axis. If it was a probability distribution across momentum space, that wouldn't work so well. But because our wave function is describing a probability distribution across the S-axis, S hat and S, that is the operator for classical position, and classical position itself are the same thing. Kinetic energy is not so fortunate. The kinetic energy operator is distinct from a particle's kinetic energy. But the kinetic energy of a particle and the kinetic energy operator are linked, and particularly we pick the kinetic energy operator to be the linear operator in an eigenvalue equation, such that when it acts on a free particle, so not a stationary state particle, this is very important, but a free particle, we get an equation for the kinetic energy of that free particle that agrees with classical mechanics. That is, for a free particle, the kinetic energy operator guarantees that the kinetic energy for the free particle will always be measured to be a half mv squared. And the form that this kinetic energy operator then has to have is this form. Now, h bar is a constant in quantum mechanics, and m is the mass of the particle. Now, as I say, if the kinetic energy operator acts on a free particle, then we get the classical equation for kinetic energy of that free particle. But a stationary state particle is almost the opposite. Well, at least some stationary states are in an extreme case. I mean, for example, particles trapped in an infinite potential well, so far from being free, are examples of stationary state particles. And for them, the kinetic energy does not obey the kind of classical relationship between kinetic energy and velocity. At least if we're thinking of velocity as the rate of change of the particle's average position with respect to time. But now we've got this kind of operator for kinetic energy, we can apply it to all kinds of particles, including stationary state particles, and use it to find the average kinetic energy. So the form of the average kinetic energy is very similar to the form of the average position of the quantum particle along the S-axis we had before. It's just when we're dealing with kinetic energy, it's important we distinguish between a observable value for the kinetic energy and the kinetic energy operator. So I'm putting a hat above the T in the integrand to emphasize that in the integrand we have the operator for kinetic energy defined in box 2. And so we now like to find the kinetic well, the average kinetic energy of our stationary state particle. We need to worry about how the wave function S how the wave function psi varies with respect to s, because the kinetic energy operator is going to differentiate our wave function. Well, it's going to actually take the second derivative of a wave function with respect to s. So we really need to think about properties this wave function will have in terms of s. Now, one thing is for stationary state particles, they're described by real wave functions. At least the wave function describing the probability of locating a particle at a point in space, or in a region in space, I should say, that wave function can be described by a real function. Now, the full wave functions, if we're going to take time into account, even though time doesn't play a role in the probability of finding our particle somewhere, nonetheless, if we were going to take time into account to get a full wave function, then the full wave function would not be real, and so it could still satisfy Schrodinger's equation. But our kind of time-independent spatial wave function, if you like, is allowed to be real, and for a stationary state particle, we can always find a real wave function for it. At least, spatial wave function. And because of that, the complex conjugate of our wave function is the same as the wave function itself, because the wave function has no imaginary component. And the only thing that differs something from its complex conjugate is an imaginary component. And so to simplify matters, I'm going to drop the complex conjugate notation in our first psi term, bring us to this. Now, in our integrand, I've replaced the partial derivatives of the kinetic energy operator with ordinary derivatives, because the kinetic energy operator is acting on a wave function entirely given in terms of s. There is no time component to our spatial wave function, and we can do that because we're dealing with a stationary state. And so we can replace partial derivatives with ordinary derivatives because there's no ambiguity in terms of what we are differentiating with respect to, because our wave function is only written in terms of s. Now we need to evaluate this integral, and there are various ways to do it. But one of the key things to note is we've got a second order derivative of a wave function in an integral. That's kind of messy to interpret or deal with. So one way we can at least reduce the order of differentiation is if we express our integral in a more bulky form using integration by parts. And that will at least reduce the order of differentiation, so we won't have any second order derivatives anymore. So if you do the integration by parts, you end up with this expression. So now, to find the average kinetic energy, all we need to do is evaluate this. Now, this looks really complicated. It's worth saying it's a lot easier than it looks if we make use of certain boundary conditions. We've actually done the hard stuff already when doing integration by parts. Now it's a fairly straightforward matter with the help of boundary conditions we will go over. But to try to make this equation be a little bit more friendly, here's the equation giving a nice kind of little Mexican wave. Now, I don't know if that made the equation look more intimidating, but anyway, that's my attempt for the equation to say hi. And for this video, the key equations will be in purple. So that's a way to differentiate what is important and what is not so important. But very important equation, thought give it a wave. But now let's move on to finding boundary conditions to help us evaluate this rather bulky looking expression. So we've had a really kind of long or bulky expression for the average kinetic energy, but fear not, for the joy and salvation of all of physics is with us, and I am speaking of boundary conditions. Physicists love boundary conditions because they make our lives so much easier. Because in many cases we can set certain things to zero, and zero has the lovely property that if we add something to zero, we get back the original thing. So we like if things vanish to zero, and that's what we will do to our square brackets that we got when doing integration by parts. So let's kind of explore the physics of the boundary conditions we want to impose upon this rather bulky expression for the average kinetic energy of our stationary state quantum particle. Bit of a mouthful there, but worth kind of emphasizing what we are doing. Well, when thinking of stationary state particles, there are a wide variety of stationary states we might want to pick. At the end of this video, we will talk a little bit about Gaussian stationary states. But one stationary state which is really nice to pick is an infinite potential well. Because with an infinite potential well, we can think of our particle as being confined entirely to a kind of segment of our S-axis between S1 and S2. Now, if it's entirely confined to that region, then logically we can't find the particle outside of that region, and so the probability density outside of the region of S between S1 and S2 becomes zero, and then using the fact that the wave function is continuous, that allows us to say that the wave function at S1 and S2 is zero. So that's kind of a summary of how we get our boundary conditions. And then the first bit of this part of the video kind of goes through that more carefully. Now it's worth saying, if we don't want to use an infinite potential well, we don't have to. We can consider the S-axis to be infinite and the particle having a probability to be found anywhere along the axis. And we might want to do that if we're considering a particle in a finite potential well and considering effects like quantum tunneling. The only slight complication with taking that approach is then S1 and S2 need to be infinite for the boundary conditions to be that psi at S1 and S2 is zero. And dealing with infinity isn't particularly ideal, so to make matters simple, I'm considering S1 and S2 to be at a finite distance apart, so we're dealing with a stationary state particle whose wave function is a wave function for a particle in an infinite potential well. But the logic being used can be extended to other stationary state particles. So as I say, if we are confining our particle entirely within the region between S1 and S2, then the probability density function outside of that region has to be zero. And because we get the probability density function from the wave function also has to be 0. And since probability density functions have to be continuous, because if they're not continuous, we have two different probabilities at the same point in space, which doesn't make any sense. So because the wave function is continuous, as is required to get a continuous probability density function from it, if psi is kind of 0 outside of the region, then psi at S1 and psi at S2, so at these boundary points, if you like, also has to be 0. And the brilliant thing is, that means if we look at the blue box 1, then our brackets in squares, kind of, our square brackets, they're going to vanish. That entire term is going to go away, because that term asks us to evaluate psi at S1 and psi at S2. And we don't even care what the second derivative is, because we're multiplying the second derivative at S1 and S2 by psi at S1 and S2. But psi at S1 is 0, psi at S2 is 0, so that whole square bracket term goes away, and we are left with a rather neat expression for the average kinetic energy of our stationary state particle. Now we need to evaluate this, or make some conclusive remarks about the average kinetic energy. Well, for a stationary state particle, psi is given by a real function, and S is the position of a particle along the s-axis. I said S slightly too much in this video. I think I'm beginning to get it a bit tongue twisted, but S is the position along the s-axis, and therefore clearly S is going to be described by a real number. So we are differentiating a real function in terms of a real variable, and therefore d psi by ds is itself going to be a real function. And therefore the output of that function when squared is always going to be positive. Importantly, it's never going to be negative. And therefore, since we are integrating a function which is always positive, the kinetic energy of our stationary state particle is going to be positive. Now you might go, well, okay, d psi by ds when squared can't be negative, but why can't it be 0? Well, the reason it can't be 0 is this. Remember that psi at S1 and psi at S2 is 0. Now, if the gradient between S1 and S2 was 0, then psi wouldn't change between those boundary points. So if d psi by ds was 0, then psi would remain constant between those boundary points. So psi would be 0 between those boundary points. And so we would have a stationary state particle whose wave function is 0 between S1 and S2, and also outside of that region of our S-axis. In other words, we would have a particle whose wave function is 0 everywhere across the S-axis, so we wouldn't be able to find the particle anywhere. Now that doesn't make any sense. The wave function can't be 0 everywhere, because we have to find the particle somewhere. It's not vanishing from existence, and therefore d psi by ds can't remain 0 across the entire region between S1 and S2. and therefore not only is the average kinetic energy non-negative, it is positive, it is bigger than zero. So that's just a technical note worth making for those of you wondering. So in summary, we have these 2 points. Rather bizarrely, as I've defined the classical kinetic, as I define the classical velocity to make, you know, the velocity as close as we can get to the classical notion of velocity. The classical velocity of a stationary state particle is 0, but it has positive non-zero kinetic energy. So what's going on? How can both of these things be true? Well, we've shown it mathematically, and that's one argument, but I don't feel that's very satisfying. So we're going to finish this video by looking at Gaussian states and using them to think about why we would be okay with such a bizarre, almost a lack of correlation between classical velocity and average kinetic energy, but we can do even better than that. We're going to use the form of Gaussian wave functions to argue that we would expect the kinetic energy operator, even for stationary state particles, to be given by a second order derivative. And so, I think the last part of this video is very informative, because at the moment we've only really properly justified the form of the kinetic energy operator in terms of free particles, but now we're going to think about why it makes sense to use this form of the kinetic energy operator to describe stationary state particles. So I've justified so far mathematically why the kinetic energy should be related to a second order derivative. And we began really this argument by considering free particles. We said we choose the form of the kinetic energy operator, T hat, to be such that when we use it as a linear operator in an eigenvalue equation, we produce an eigenvalue for a free particle which agrees with the classically expected kinetic energy of the particle. So T hat yields an eigenvalue which matches the classical formula for kinetic energy, so half mv squared effectively. But then we took this operator and applied it to stationary state particles. Now, a free particle is not a stationary state particle. And one of the key differences is kind of like a free particle has a wave function where we can't really separate the position s and time t, whereas we can separate those two variables if we're considering stationary state particles, thus allowing us to define a spatial wave function psi of s which is independent of t. So how should we interpret the kinetic energy operator as a second order derivative when applied to stationary state particles? So when we're applying the kinetic energy operator to particles which most certainly are not free. And this will give us some explanation for why the kinetic energy operator is a second order derivative in a very general case. Now to do this, I'm going to be looking at a group of wave functions which are stationary state wave functions, so that is the wave function is time independent. But to make matters fun, and because I love a particular kind of curve, as most of the mathematical community seems to also love, I'm using Gaussian curves for this last part of the video. So Gaussian curves are not the kind of curves you would see for particles in an infinite potential well, but these are valid, stationary state wave functions. They're wave functions in terms of S, and they're normalizable, which is all we really need to have a valid stationary state wave function. Oh, and also they vanish at plus or minus infinity. So here we have a few different Gaussian curves. And in a hypothetical scenario, each of these curves could be a good fit for the wave function of a stationary state particle. And here we have 4 curves. We usually did it with 3, but I wanted maximal colour, so we've gone for 4. I also like even numbers. But anyway, these curves have a similar kind of shape. They both kind of peak at the same value. But some are very narrow and some are more broad. So as we go from the broadest Gaussian curve, so the one with the standard deviation sigma of 16, to the Gaussian curve with a standard deviation of 1, the orange dash golden curve, we see that the curves kind of like become more narrow. And so if we're thinking in terms of wave functions, the probability of finding a particle in a region of space becomes less and less distributed across that space as the standard deviation of the Gaussian wave function decreases. And that's an important observation. And we'll be kind of like building on that to justify the form of the kinetic energy operator. And when doing this argument, mainly because it's helpful in terms of making it presentable and not having really bulky fractions in the middle of texts, I'm going to use the notation given below the chart for a second order derivative. This is a kind of notation seen in advanced physics and mathematics topics anyway. So using this notation, we can make these 2 points, which the first one I made. The second point, that the average value of the second order partial derivative of psi with respect to S increases as the standard deviation decreases, is a more technical way of saying what I've already said. And to see that, let's think about mathematically how we would measure how narrow a peak is. So if a peak is very narrow, then the gradient of that peak is changing very significantly over our value of S. It changes very significantly indeed. Whereas if the peak is very broad, then the gradient of the peak changes very gradually across S. And that justifies the idea that if the standard deviation is small, so the peak is very narrow, then the kind of average value of the second order derivative of psi is going to be very large. Or at least the second order of the kind of like magnitude of our wave function. Although we're dealing with kind of real functions, so it doesn't really matter here. Now you might go, well, is the average value 0 because the curve is increasing and then decreasing and gradient, but you get what I mean. I might be being a bit lax here, but the I suppose I should say the average value of the magnitude of the second order derivative of the wave function is very big if the standard deviation sigma is very small. And therefore, well, that's one point to make. So we see that sigma, the standard deviation, is related to the second order derivative. But how does sigma relate to kinetic energy? And that will then allow us to relate kinetic energy to the second order derivative. Well, as sigma drops, the peak becomes more narrow, so the particle becomes more localized. So there is a smaller uncertainty in the position of the particle. That is, there is a smaller region over which the wave function is appreciably non-zero. But by Heisenberg's uncertainty principle, if delta S is small, then the uncertainty momentum delta P is going to be pretty big. So a small s allows for a particle to have a lot of kinetic energy. Sorry, a small delta s allows for a particle to have a lot of kinetic energy. So in summary, if psi is small, the average second order derivative of the wave function is big, and if psi is small, the kinetic energy of the particle is big, so it makes logical sense that the kinetic energy is proportional or related to a second order derivative of a stationary state wave function. Now, yes, I've used a Gaussian wave function, but it gets my point across well, so I'm happy to just use a stationary state example with a Gaussian curve and then just encourage you to explore further if you would like to see more examples of this principle. That the second order derivative tells you about the kinetic energy of a particle. Now notice we can use Heisenberg's uncertainty principle and a diagram of the wave function to arrive at the relationship between kinetic energy and derivatives. But we didn't have to bring in the concept of time. And due to not bringing in the concept of time, the kinetic energy of a stationary state particle is very unrelated to partial derivatives with respect to time. So our argument allows us to ignore time essentially, and therefore we wouldn't expect classical velocity to have any strong connection to the kinetic energy of a stationary state quantum particle. Now that was a bit of a mouthful. There's been a few mouthfuls in this video, but I think it's a really interesting topic, particularly because kinetic energy is one of the first things you learn in school. So I think it's good to have a video that kind of shows the concept is a lot more nuanced than it might at first seem, to emphasize how mysterious the universe truly is. Now, I wish you a fantastic Christmas, hopefully a little bit of snow, and as always, keep exploring the universe. Keep an eye out for a Christmas quiz on this channel, and looking forward to seeing you in the new year for some more wonderful physics.